Hi, everyone. Thanks for joining my talk. My name is Guoqing, and today I'm going to talk about our recent work on addressing data-efficient machine learning with meta-learning. Operation language models has gained a lot of attention in the NLP research community, and also it helps obtain better performance on a lot of downstream tasks. But this is at the cost that we need to have a lot of labeled data. For example, in this plot, I'm showing the performance of a fine-tuned BERT model on this QQP dataset, which is a sentence similarity task. And you can see that actually in order to obtain above 80% performance, we actually need more than 300,000 examples. So this is clearly not the case for a lot of actual applications or domains there where we only have a very limited amount of labeled data. In this work, we try to look into the auxiliary information, or which is so-called proxy supervision, to help tackle those tasks here. And these different signals can come from either noisy labels or automatic labels, or even like human rules. And these are typically much easier to collect than those manually annotation data. So how do we leverage such data? And our idea is that we're going to use meta-learning to model and transform such data. And the key idea is that with the different type of data available, and we're going to build a meta model to transform those data such that this can be used by our task model. Let's take the example of using weak supervision as a case here. On the right-hand side, I'm showing a general framework of how we can use meta-learning to leverage such data. For example, we are given a set of small, clean examples and also a large set of proxy examples here. And our goal is to train a task model. And the way we do this is that in addition to the main task model, we are also building a so-called meta model. And in this case, this is a label correction network, which takes the noisy data and tries to produce a corrected label. And this corrected label is going to be used by the main task model to train. So without the direct mapping between the noisy labels and clean labels here, there's no way that we can tell how well this meta model is trained here. The way we do this is that we're going to take the trained main model and evaluate its performance over this clean data, so such that this loss of performance can be used as a feedback to backpropagate to update our meta model here. So this essentially boils down this entire framework to this bi-level organization process, which is also very similar to classical meta-learning. So essentially, in the outer loop, we're going to minimize the loss of the trained model over this small set of clean data, whereas in the inner loop, our main model is trained to minimize the training loss over this transformed data from the meta model. Let's take a deeper look into this framework. So in this plot, I'm showing the detailed architecture of this framework for using meta-learning to leverage correct labels here. On the left-hand side, this is the label correction network, which takes the noisy features and also its weak labels as input and tries to produce the correct labels here. And our main task model is taking that as data and training its own parameters. And then the main model is evaluated over this small set of clean examples here. And this entire loss can be used to update our meta parameters here. And the insight we're using here is that we believe a good label correction network is able to produce better corrected labels such that the main model can benefit from that, and so that it can produce a better model which can perform well on this clean set here. So how does this perform in actual evaluations here? So we conduct experiments over different data sets, including both text classification and also image recognition. Across this broad set of data sets here, we compare with two classic methods. One is to also use meta-learning to assign different weights or importance to the examples in the weak set. And the other one is to leverage label correction, but it's based on estimating the label corruption matrix based on the two sets of data. And you can see that actually with the proposed data-driven approach, our method is able to achieve better performance in terms of leveraging weak supervision to improve the task performances. And beyond just working with meta-learning with weak supervision, we also extend this work onto multiple settings, including how to use this to model and leverage data from a different domain or different language. Also, how to use this to leverage even unlabeled data. With that, there's still a lot of challenges going forward and also questions unanswered here. For example, one thing that we can do is that to understand what is the best data sources for this meta-learning framework, and also to understand to which extent that this meta-learning framework can help us in transforming data here, and also how to make this framework to work with even more complex settings like structure prediction or generation here. And the other factor is that because of meta-learning nature, the computation of this meta gradient requires approximating to these second-order gradients, so efficiency could be an issue for some cases. And also recently, there are some new training paradigms involving reinforcement learning and also problem learning. How to best combine the machine learning framework with such training paradigms to achieve a better performance is also an interesting direction to go here. And also, in order to better evaluate such models, having benchmarks available on this fusion notion or weak supervision part will also be very valuable to the research community there. So I think that pretty much summarizes my talk. Thank you for joining my talk, and also thanks to all my collaborators in all this work. And if you're interested to discuss more, please feel free to reach out to me offline. Thanks.